Welcome to this explainer. I want you to imagine, just for a second, a research and development lab that's been running 24/7 for 3.8 billion years. It's got an unlimited budget, infinite test subjects, and a literally ruthless quality assurance process because, well, failure means extinction. I'm talking, of course, about the natural world, driven by the process of evolution. Today, we're going to dig into the absolutely brilliant engineering blueprints that nature has perfected over those billions of years and explore how we are finally learning to copy them. Here's the roadmap for our masterclass today. We'll start with Section 1, Introduction to Biomimetics. Then, Section 2, Mastering Surfaces and Adhesion. Moving on to Section 3, Aerodynamics and Fluid Flow. Section 4 will cover thermodynamics and passive cooling. And finally, Section 5, Nature as the Ultimate Innovator.
All right, Section 1, Introduction to Biomimetics.
So what exactly is biomimetics? Also known as biomimicry, it's defined as the study and imitation of complex biological entities, macroscopic forms, and natural processes to solve human engineering and design problems. Now, I want to emphasize a really vital distinction here. We are not just talking about aesthetics, okay? We're not simply making things look like nature. No, we are looking to nature for precise mechanical, chemical, and physical solutions to solve incredibly complex mathematical and structural engineering problems. Okay, let's dive right into this with Section 2, Mastering Surfaces and Adhesion. Let's consider the common burr. If you've ever walked through a field, you've definitely had these annoying little things stick to your clothes. But if you analyze their structure, you'll see this isn't some random accident. It's perfectly, mathematically designed. The exterior is covered in these tiny rigid hooks that are geometrically optimized to catch and latch on to passing fibrous materials, like animal fur or human fabric, all just to disperse its seeds. And this brilliantly illustrates the basic physics of mechanical interlocking. Back in 1941, a Swiss engineer actually put these very same burrs under a microscope and recognized the potential for a reusable mechanical fastening system. He translated that natural hook blueprint into the synthetic loops and hooks that we all know today as Velcro. It's a purely structural solution to temporary adhesion, meaning it requires zero sticky adhesives or chemical bonds. Now, what's really interesting about the gecko is that it solves the same problem of adhesion, but through a completely different, way more advanced physical principle. While the burr relies on macro-level mechanical hooks, the gecko's foot allows it to effortlessly scurry up sheer vertical glass by exploiting physics at the molecular level. Let's break down the exact mechanics of how this works. Step 1. The gecko's toes are absolutely covered in millions of microscopic hair-like structures called microsetae. These are flexible enough to perfectly conform to the microscopic imperfections of literally any surface. Step 2. Because they get so incredibly close to the surface, they trigger what are called van der Waals forces. These are essentially weak intermolecular electrical attractions. But when you multiply that by millions of setae, it generates massive adhesive strength. Finally, Step 3. To actually move, the gecko simply alters the angle of its foot, directionally peeling the setae away to instantly break that molecular bond. By really understanding those specific molecular interactions, engineers were able to translate this exact biology into a synthetic bionic tape. By manufacturing microscopic synthetic bristles that mimic the gecko's microseat, we can now create incredibly strong, completely reusable adhesive tapes that leave absolutely no sticky chemical residue behind. It's a massive leap forward for materials science. Shifting gears to another surface marvel, let's talk about the lotus leaf. You know, the lotus thrives in these muddy, swampy waters, and yet its leaves always remain perfectly pristine. Why? Well, it's due to a property called superhydrophobicity. At the microscopic level, the leaf is covered in a complex nanostructure of tiny bumps coated in natural wax. This distinct geometric pattern minimizes the contact angle between the leaf and a water droplet, physically preventing the fluid from wetting the surface. Instead, the water just beads up perfectly into tiny spheres. And when those perfect spheres of water roll off the lotus leaf, they pick up dirt along the way, effectively making the surface self-cleaning. By replicating this exact topographical nanostructure in the lab, engineers have actually developed superhydrophilic and superhydrophobic industrial coatings. It's just wild to think that a plant from a swamp inspired the biocoatings we now use on everything from self-cleaning windows and highly efficient solar panels, all the way to water-repellent fabrics and rust-resistant car parts. Moving right along to Section 3, Aerodynamics and Fluid Flow. Let's examine the geometric profile of the kingfisher. This bird has to dive from a low-density medium air into a high-density medium water to catch a fish, and it has to do it without creating a splash that would scare off its dinner. The mathematical shape of its beak, which is basically a wedge that gradually increases in cross-section, is perfectly engineered to displace fluid smoothly. It entirely eliminates the sudden pressure wave that typically causes a splash. Now, early designs of the Japanese Shinkansen, the famous bullet train, actually had a massive engineering flaw. As they forced their way through tight tunnels at ultra-high speeds, they built up this massive wave of atmospheric pressure, which resulted in a deafening sonic boom right as they exited. But by applying the precise mathematical geometry of the kingfisher's beak to the nose of the bullet train, engineers completely solved the problem. The redesigned bionic nose sliced through the air pressure seamlessly, entirely eliminating the sonic boom while also increasing speed and reducing power consumption. Pretty amazing, right? So, nature effectively utilizes three distinct mechanisms to reduce drag in fluid dynamics. First, there's the generation of microturbulence to keep boundary layers attached. Second, macroscopic vortex control to manage wake and fluid flow. And third, utilizing streamlined, sometimes totally counterintuitive, geometric forms to lower overall resistance. Keep this framework in mind as we look at our next few aquatic examples. When automotive engineers wanted to design a highly aerodynamic, fuel-efficient vehicle that still had maximum interior volume, they surprisingly didn't look to sleek sports cars. Nope, they looked to the seemingly clumsy boxfish. Despite its paradoxically cube-like shape, the boxfish's rigid exoskeleton causes fluid vortices to form in places that actually stabilize the fish in turbulent water, all while keeping its drag coefficient remarkably low. Mercedes-Benz mimicked this exact structural profile to create their bionic car concept, absolutely proving that unconventional natural shapes can yield staggering aerodynamic efficiency. Going back to that concept of microturbulence, let's look at the apex predator of the ocean, the shark. A shark's skin isn't actually smooth. It's covered in these microscopic, tooth-like scales called dermal denticles, which feature tiny longitudinal ridges, or riblets. These riblets purposefully induce a thin layer of microturbulence right at the skin surface. And paradoxically, that reduces the larger drag-inducing friction of the bulk water flowing past. Applying synthetic riblet films to the hulls of marine vessels, and even the fuselages of commercial airplanes, drastically reduces drag, which radically increases both speed and fuel efficiency. But fluid dynamics isn't just about moving through water, it's also about moving the water itself. The macroscopic logarithmic spiral of the calla lily flower is a geometry that pops up constantly in nature to manage fluid flow. By biomimicking this exact spiral geometry, engineers developed a revolutionary bionic fluid impeller. Instead of just slapping the water like a traditional fan blade does, this bionic impeller induces a natural vortex. It can mix and move immense volumes of water using just a fraction of the energy and with almost zero cavitation. All right, let's shift to section 4, thermodynamics and passive cooling. Consider the towering termite mounds found in Africa. Despite the intense, wildly fluctuating heat of the external environment, the fungus these termites farm inside requires a very strict, constant internal temperature to survive. They achieve this through an absolutely brilliant feat of passive cooling. The mound is built with a complex network of internal flues and chimneys. As the wind blows across the top, it creates a pressure differential that actively pulls the stale, hot air up and out while simultaneously drawing cool air in from the bottom. It effectively creates a completely natural, self-sustaining air conditioning system. So, the crucial point here is the massive contrast in efficiency. Traditional human architecture relies heavily on brute force mechanical HVAC systems, massive air conditioning units that require immense amounts of electrical energy just to forcefully push chilled air through rigid, inefficient ducts. But biomimetic structures, mimicking that termite mound, leverage basic thermodynamics like convection currents and pressure differentials to achieve vastly superior passive airflow dynamics, all with a drastically lower energy footprint. And this isn't just theoretical. It scales perfectly to massive human structures. The Eastgate Center in Zimbabwe is a huge commercial building that was structurally modeled directly after the airflow dynamics of the termite mound. By utilizing heavy masonry for thermal mass and a series of bio-inspired chimneys and vents, the building literally cools itself passively. It uses less than 10% of the energy of a conventional building of its exact size. Nature's blueprint scaled flawlessly into modern human architecture. Bringing us to our final part, Section 5, Nature as the Ultimate Innovator.
To wrap up our masterclass today, I think we really need to start viewing the natural world differently. Biomimetics proves that nature isn't just a source of raw materials or aesthetic inspiration. It's an exhaustive, highly detailed catalog of proven, mathematically optimized engineering solutions that have literally survived billions of years of rigorous field testing. From the molecular adhesion of a gecko's toes, to the aerodynamic perfection of a kingfisher's beak, all the way to the passive thermodynamics of a termite mound, we are just barely scratching the surface of translating these organic patents into our own technology. So, I want to leave you with this final, provocative thought to carry with you. What other seemingly insurmountable engineering problems currently facing humanity could be solved by simply looking out the window? Thank you so much for joining me for this explainer, and keep observing the world around you.